Bubbles perfectly illustrate the physical phenomenon known as thin film interference.
Thin film interference occurs when light must pass through different media with different indices of refraction.
Basically, some light is reflected on the surface of the film, here, the bubble, and some light must pass through the oily layer, also the bubble, before being refracted.
Remember that the thickness of the film must be on the same in the same phase as the light being refracted in order to see the interference, which is why you'll have dark bands and light bands.
We said that the thickness of the film has to be on the same order of magnitude as the wavelength of color that it's reflecting. So what this means is basically when we start seeing all these colors in the bubble, it means that the thickness of the bubble at that point is somewhere along the lines of 400 to 700 nanometers, because that's the visible spectrum of light. We can start to see some of these colors here, and that's where the light is being reflected.
Notice the banding pattern on the bubble, and it's slowly changing, it's slowly going down as
Are
gravity takes the
Are those some Newton rings that I see? We've got to kind of wait a little while for gravity to take over and make the film thinnest on top for these Newton rings to appear. But basically what the Newton rings are is a particular banding pattern of the colors based on the thickness of the film. So we're going to see kind of a striation in the bubble. And here we can start to see it. Can you come put it down a little bit? Okay, so right here, I'm trying to pop it right there. You can really see that striation.
happens in a repeating pattern as the lens gets thicker and thicker because it's an integer multiple of the wavelength of the light, or lack of light, as the case may be.
Look, we also have our concentrated light right there as the lens. Who knew bubbles could be so much fun?
Every child ever.
The original experiment with Newton's rings was having a curved glass on top of a flat glass. But the principle is the same here. As time goes on, gravity pulls more of this oily film downwards, right, Brian?
Right, and it eventually will pop because it's so thin at the top, but you can see the lines move down and compress.
Exactly. See, they've moved down just since we've been talking. And if I held this here, they'd keep moving down.
And this is actually in a different light than we were showing you earlier. We were going to try to see if the spectrum of the lines was different, the pattern was different, but it appears to be the same pattern, just easier to see.
Definitely easier to see. And so this type of light bulb, I know you've all heard of the GE Reveal light bulbs. You know, they're supposed to be natural sunlight. And so we looked at the light under a polarizer. Let's see if we can, here's the polarizer. Just basically it diffracts the light. So what we're going to do is we're going to try to look at the light and split it into its component wavelengths. There we go. Look at that. You can see all the component wavelengths of this light. And see, there's still a lot of white light. So let's see if we can go to another maximum. There we go. See, this is the second order maximum. This is the first. It's still pretty powerful. So we're gonna go to the second order maximum, and we can see a little more clearly how the light breaks. So on the picture, they always show that it's every color of the rainbow. Well, looks like red, green, and blue to me. I'd be missing a few. Maybe they're in the first maximum. Alright, so back to the bubbles.
Because the index of refraction of the bubble is higher than the air, there's a phase shift automatically, and so the thickness of the bubble should be 1/2 plus the order times the wavelength divided by 2.
Exactly. And remember how we saw that the first order wavelength was really bright, so we had to go to the second one.
The dark bands you see are where the light adds destructively, and the bright bands are where it adds constructively at different wavelengths.